In this video, I want to take a look at the notion of one-to-one and then how that leads to invertibility of transformations. Okay. Now, you may have seen the concept of one-to-one in the past. I certainly know that we talk about it, but we don't use it a lot. We talk about one-to-one functions, right? Well, here's the definition I'm going to give. A transformation is said to be one-to-one if T of u equaling T of v implies that u equals v. That is, if ever you have 2 points looking like they're being sent to the same point, right? If you've got 2 points here, u and v, and if they're equal to each other, then that means u has to equal v, which means if they're not equal to each other, then they have to be sent to 2 different points, right? So this would be one-to-one. Whereas if you had something like this, where you had 2 different points being sent to the same point, this is not one-to-one. Right? And I do the 1-1 as an abbreviation for one-to-one. It can't just be for some u and v they're being sent to different points. It's like every time you have 2 different points, they get sent to 2 different points. Okay. Or if ever you have 2 things being sent to 1 point, then those 2 points really weren't 2 points. They were 1 point to start with. Okay? That's one-to-one. Right? When we talk about functions, I know like in a trig class, when we start talking about inverse trig functions, of course, trig functions aren't really invertible because they're not one-to-one. They don't pass a horizontal line test, right? You look at like y equals x squared, right? That there's places where you have a horizontal line hits the graph in 2 spots, which means there's 2 x values that give you the same y value, right? That's not one-to-one. So the textbook we use here for this linear algebra class actually gives this definition in terms of a matrix transformation, T sub A, but the notion of one-to-one is far beyond that of just matrix transformations. It's any functions or any transformation, any mapping from one space to another space. If it sends distinct points to distinct points, then it is one-to-one. Okay. Examples of transformations we've already looked at that are one-to-one: rotations, reflections, shears, most expansions and most dilations. I say most. The book would say all, because one of the things the book didn't do is for the expansions and the dilations, they always took positive values of k, right? That you started with your expansions, right? You either stretched or you called it a compression and it collapsed, or maybe it was out of a contraction. I don't know. I still think of it as expansions, but by factors less than 1. So, and I also, for me, it was okay to have negative 1. You know, you could have a compression that's so much that it actually goes the other way, or an expansion that gets you, backwards. That was both an expansion and a reflection. Right? But if you're going to allow negative values of k, well, how about the value 0? And so if you had an expansion that was multiplying, say, in the x direction by 0, you would have a projection onto the y-axis. Likewise, if you're going this way and you're expanding by a factor of 0, then you'd be projecting onto the x-axis. And that is not one-to-one, right? Not one-to-one are the projections. Because, if you're projecting down onto the x-axis, you might have 2 points that both go down to the same spot, right? They were in different places, but they end up with the same y-coordinate of 0. So projections are not one-to-one, but these other ones are, right? And again, by the most here, that's as long as you're not multiplying by 0, right? K can be anything but 0. Change of basis transformations we did a little earlier in the course, right? We used a matrix to change coordinates with respect to base B into coordinates with respect to base B prime. Those were one-to-one. So there's a couple other definitions here that go along with this. Just again, the book gives these definitions in terms of matrix transformations, but really this is any transformation from a vector space to another vector space. Doesn't necessarily have to be matrix 1. So if T from V to W is a transformation, then we call the kernel of T and we denote it Kernel of T, is the set of all vectors in the domain such that they are sent to the zero vector in the codomain. Right? So it's the set of all V such that T of V is equal to the zero vector. That's called the kernel. And if you've got a transformation from V to W, we define the range of T as the set of W in the codomain such that T of V equals W for some V, the things that get hit. And I believe we've defined the range before. Okay. Now, again, the book is defining this in terms of T sub A, some matrix transformation, but the notion is good for any transformation from one vector space to another. It has to be a vector space because you got to know what a zero vector is. It can't just be one set to another, because if there's no sense of zero, then this doesn't make any sense. These notions are actually very similar to things that we have done before. So if this transformation actually is a matrix transformation, where TA goes from Rn to Rm, so A would be an m by n matrix, then the kernel and range are very closely related to other notions that we've talked about this quarter. And in fact, we can think of this in terms of matrices or systems or transformations, right? That this new notion of the kernel is exactly the same thing as the null space, right? I mean, how do you do a matrix transformation? You multiply by the matrix A. So to say that T sub A of x equals 0 is the same thing as saying A times x equals 0 vector, which was what it takes to be in the null space of A, right? But that's also, from the system point of view, the solution space of the homogeneous system, AX equals 0. So there's three notions here that are the same thing, but sort of put into different settings, right? There's the matrix setting, the null space of the matrix. There's the system setting, the solution space of the homogeneous system, or the transformation setting of the kernel of the transformation. Either way, this is the stuff that when you multiply it by the matrix A, gives you zero vector as a result, right? And that's all happening in Rn. That's in the domain space, right? On the other side here in the codomain, there's the following three notions that really are the same thing. From the point of view of the matrix, you have what's called the column space, right? The span of the columns. From the point of view of the system, you have the set of vectors B such that AX equals B is consistent, right? And from the transformation view, you have the range. These are the things, these are the B's that when you multiply, that somehow give you, for some X, you get B as an output, right? And that, as it turns out, is the same as looking at what's in the column space of A. What things are linear combinations of the columns. Because when you multiply by X, what you're doing is you're taking the components of X and multiplying by the corresponding columns and adding them up. So you're taking linear combinations of the columns here. So those two notions are talked about in three different ways here in this course. Let's jump down here. So that actually leads us to a nice theorem. A theorem that perhaps you could see is tied to stuff we've done before. If A, what's going on there? If A is an n by n matrix, so a square matrix this time, and T sub A is the corresponding matrix transformation from Rn to Rn. Actually, it's a matrix operator. It is a transformation, but remember, if your domain and codomain are the same space, we call it an operator. Then the following statements are equivalent. A is invertible, right? You have an invertible matrix. The kernel of the transformation is just the zero vector. The range of the transformation is all of Rn, and TA is 1 to 1. Okay, so the transformation is 1 to 1. The proof, I'm just going to talk it through, but in order to prove this, the way we do it is I'm going to show that statement 1 implies statement 2, and then I'm going to show statement 2 implies statement 3, and then statement 3 implies statement 4. Okay. Now the textbook does the first two written out and leaves, you got to get all the way back to the beginning, come to think of it, 4, and then has to imply 1 again. Right. So the book does this one and this one. It leaves these two as exercises. I think I'm just going to talk my way through all of them. Right. The thing is, we already know a lot about A being invertible, right? It's equivalent to a whole bunch of stuff. Well, one of the stuff is A is invertible implies that AX equals 0 has only the trivial solution. Well, if AX equals 0 has only the trivial solution, that means, right, AX equals 0 implies that X equals 0. Well, this right here is TA of X. So to say that TA of X equals 0 implies that X equals the 0 vector, that's saying the kernel is just the 0 vector. Right? If the only thing that gets you there is 0, then the kernel is the 0 vector. So 1 implies 2. I need to do 2 implies 3. If you know that the kernel is just the 0 vector, you know that the null space is just the 0 vector, and so you know that the nullity is 0, right? The dimension of the null space is 0. I also know that the rank plus the nullity is equal to n. So if the nullity is 0, the rank must be n, which means that the range space, which is the column space, has rank n. So in Rn, it must be the whole thing. Okay, so there we go. There's 2 implies 3. 3 implies 4. If you know the range is Rn, can we show this is 1 to 1? I'm going to pause for a minute. All right, so in the pause there, I did a little bit of soul searching and realized that all of my arguments for 4 were 1 implies 4. So in order to make this right, I have to get 3 back to 1 because I really want to do 1 implies 4 and then 4 implies 1. So the thing though, the range is the same as the column space. And so if the range is all of Rn, then the column space is all of Rn. But I already know that the column space being all of Rn is equivalent to A is invertible. So that gets me from 3 back to 1. Right? Now, 1 implies 4. Now, if A is invertible, then I want to show it's 1 to 1. So this is going to be 1 implies 4. Well, if I happen to have two things that get sent to the same spot, so TA of U equals TA of V, then I know that A times U equals A times V, right? Because that's what TA of U is, it's this, and that's what TA of V is, it's that. But if A is invertible, then A inverse exists, and I can multiply both sides here by A inverse on the left. And of course, A inverse times A is I, and I times U is U. So if you had two things that looked like they were being sent to the same spot, they were actually the same thing to start with. So the transformation is 1 to 1. If A is invertible, this is 1 to 1. Now, the only thing left is to show that 4 implies 1. Okay? So if you know you're 1 to 1, how do you know you're invertible? Suppose A times X is equal to 0. If X has to be 0, then we already know that means that A is invertible, right? But A times X is actually TA of X. So if if TA of X is equal to 0, then because this is a 1-to-1 transformation, I know that X has got to be 0 because the transformation, matrix transformation, always takes 0 to 0. And so they can't take anything else to 0 if it's 1-to-1. So X has got to be 0. So the fact that this is 1-to-1 means there's only one thing that can go to 0. And if there's only one thing that can go to 0, then the matrix must have been invertible. So there we go. These are all equivalent. And so they're also all equivalent to all the 50 million other things that we've already said are equivalent to A being invertible. One of the things this really does for me is to say I have a really nice way to check if a matrix transformation is 1-to-1 or is it invertible? Is the transformation 1-to-1? It's 1-to-1 if the matrix that's creating this transformation is an invertible matrix. And we know that it's invertible if the determinant is not equal to 0. So for instance, I can check my rotation matrix. Here's my general rotation matrix for rotating through an angle of theta. Look at the determinant. It's cosine squared minus negative sine squared. So cosine squared plus sine squared, which is 1, that's not equal to 0. This rotation matrix has a determinant not equal to 0, so it's a one-to-one transformation. It takes different points to different points. And that's probably not too surprising, right? When you look at rotation, right? That if these two vectors are different to start with and you rotate them, they're going to be different to end with. But take a look at, I'll do another example over on the side here, our matrix, which was, let's say, projection onto the x-axis, right? 1, 0 went to 1, 0, but 0, 1 went to 0, 0. And if you look at the determinant of that thing, well, that's 0 minus 0, which is 0. This is determinant 0 matrix. So that transformation, projection onto the x-axis, is not one-to-one, which clearly is not one-to-one because you got a whole line worth of stuff that would all be projected down to the same spot, right? And everything down here underneath would be projected up to that spot. Definitely not one-to-one. Now, we'll end this video with the following theorem. If you have a matrix transformation, TA from Rn to Rn, so A is square now, right? A is a square matrix. If this is one-to-one, then there is an inverse transformation, and the inverse transformation is the transformation corresponding to the inverse matrix, A inverse. Right? If it's one-to-one, we've already stated that A, we just showed up above that A has to be invertible, and so this transformation exists, and it is the inverse of TA. And we prove that it's the inverse just by looking at do what we think is the inverse function and the function of x, right? Do those and do it in the other order and see that what you get is x each time. But again, matrix transformation is multiplying by matrix. So if I multiply it by A and then I multiply by A inverse, well, I get back to just what I started with. Or if I multiply by A inverse first and then A, well, I get back to what I started with. And so these two transformations are inverse transformations because these two matrices are inverse matrices. And all we're doing with the transformation is multiplying by those matrices. There you go, one-to-one, which leads to invertible transformations.